In this problem, we're given what's called a piecewise defined function. It's called piecewise because each function is defined in pieces. In particular, this example has two pieces. We have the top piece and the bottom piece. And it turns out that for every input, you're only going to get one output. So these are valid functions. And they're used in situations where one function alone or one equation alone isn't enough to describe the behavior that you're trying to describe. So this is the math notation. It actually ends up being very simple when you know how to read it, but it just looks awful when you see it for the first time. So what I've done here is I've translated the math notation into words. So basically this says if your input x is less than 0, that's what this piece says, if you're going to plug a number in that's less than 0, then use the first part of the function, which is y equals 6x plus 6. So that's this table down here. So you're used to making out tables in mathematics, but the difference is that you're only supposed to use this table under the condition that your inputs are less than 0. So if your input x is less than 0, use this table to find your output. The second piece says, what if your input is greater than or equal to 0? So if x is bigger than or equal to 0, which by the way we call that non-negative in mathematics. 0 is not negative. And if you're greater than 0, you're not negative either. So if your input x is greater than or equal to 0, don't use the first part, use the second part of the function, which they're saying is 6x plus 12. So basically, you're given two different equations. Under no circumstances would you ever use both. You only use one or the other, and these are the directions when you use them. In fact, a lot of times these piecewise defined functions will have the word if in there, meaning use the second function, or excuse me, the second part of the function if x is greater than or equal to 0. So let's just do one of the parts right here. One of the questions is to find f of negative 1. So I need to decide, is negative 1 going to be plugged into this function or this function? Again, you under no circumstances ever use both. So my x value is negative 1. I have to decide, is that a number that's smaller than 0 or bigger than or equal to 0? Or certainly on the real number line, 0, if I put 0 right here, then the number negative 1 would be to the left of that. So negative 1 is most decidedly less than 0. So my input's less than 0, that means I'm going to use this table. And the rest you already know. You know how to plug an input into a function. Simply replace x with negative 1. And doing that, you'd get negative 6 plus 6 or 0. So the answer for the first one would just simply be 0. And the second piece would be just as easy. The hard part is just knowing which piece to use. Do I use the top piece of the function or the bottom piece? So I'm plugging in 0, so I have to decide, is 0 less than 0 or is 0 greater than or equal to 0? Well, obviously 0 is 0, so it satisfies this inequality. So it would not make sense for me to use this equation when plugging in 0 because it doesn't satisfy this. We're only supposed to use the first piece if we're plugging in negative x values, and 0 is not negative. So 0 does satisfy this inequality here. 0 is greater than or equal to 0. So it basically says use the second piece, and it's just as simple as plugging 0 into the second piece of the function. So you'd have 6 times 0 plus 12, and that clearly is 12. So f of 0 would be 12. The last one, f of 2, again, you start out saying, well, am I supposed to plug 2 into the first piece or the second piece? It never is the case that you do both. So is 2 smaller than 0 or is 2 bigger than or equal to 0? Obviously 2 is bigger than or equal to 0. On the real number line, 2 is to the right of 0. Therefore 2 is bigger than 0. So basically it says plug 2 into the second piece of the function. And if you did that, it would look like f of 2 equals 6 times 2 plus 12. So that would give me 12 plus 12 or 24.